distribution بالنسبة إلى شنو solid cylinder يعني هذه الأسطوانة عندها السلندر هذه solid cylinder شنو كان عندنا الأمثلة علتنا كان عندنا مثل عندنا nuclear reactor هذا شيء يمثلنا اليورانيوم element أو عندنا واير يودي تيار كهربائي أو عندنا شنو عندنا مفاعلات أو عندنا شنو chemical reaction فالعملية الذي راح تتم طبعا نقدر نوجد temperature distribution مثل ما سوينا بالمحاضرة السابقة. الآن شو راح ناخذ a hollow cylinder أسطوانة مجوفة هذا سلندر. هالهولو سلندر هم مثل لك يورانيوم element فيكون شنو temperature distribution ضمن هذا الجدار الموجود عندنا الهولو سلندر فراح نقول الشيء الذي عندنا ما يلي راح يكون عندنا شيء ما يلي الانبوت heat to the element plus heat generated within the element minus heat output equal to naught. Hollow cylinder will be on like this shape. Hollow cylinder will be like this shape. Height of the cylinder is L, and inside diameter I, where the outside diameter R subscript naught. If we take an element strip, within this hollow cylinder, QR heat inside, radius of the inside of the element R, and the heat out of this element would be QR plus D QR. Temperature distribution, it will be T and T plus dt. Thickness of this element strip, it will be dr. Thickness of this element, it will be dr. This element is strip within the wall of the hollow cylinder, Now what we say? We could say now input heat to the element, which is QR, plus heat generated within the element. What we mean by the heat generated within the element, within this element strip, minus heat output should be QR plus dQR. Why the heat change from QR to Q plus dQR? Why? Because there is a heat generated within this element strip. The input QR, the output will be QR plus dQR. This change of the heat from inside to outside occurs within this element. Now we substitute these definitions within this statement here mentioned here. Now what we are going to say, Q in equal minus K 2R pi L dt by dr. Q out will be equal minus K 2R pi L dt by dr plus d by dr, open bracket, minus K 2R pi L dt by dr times dr. Q generated will be equal to Q subscript G times 2R pi L dr. Therefore, minus K 2R pi L dt by dr minus K 2R pi d L dt by dr plus d by dr minus K 2R pi L dt by dr times dr. This of course will be equal to Q subscript G 2R pi L dr equal to naught. Therefore, the Q subscript G times 2R pi dr L plus d divided by dr into K 2 pi R L dt by dr equal to naught. Let's see now this one. Our statement is like this. Input heat to the element strip. Heat input to the element strip QR plus heat generated within this element minus heat output equal to naught. Now I'm going to put our statement in terms of mathematical model. This equation, of course, is Fourier equation. Q equals minus K A dt by dr. This is Fourier equation. This equation represents heat transfer by conduction through a cylindrical shape. Now what we are saying now, Q in equal minus K, the thermal conductivity, physical properties of the material. Now what we're saying about A, you see now there are there are two aspects. There are two aspects to find the heating surface area. What we said, we started in the beginning of our lecture, we said we have a hollow cylinder. A hollow cylinder. This is a hollow cylinder. Now, if I want to find the surface area of this elementary surface, what I'm going to say the circumference of this cylinder times the height. It will give me the heating surface area. The circumference or the perimeter of this cylinder, it will equal the length of this flat surface. I repeat this one again. The perimeter of this cylinder would equal to the length of this circle. If I open now this cylinder, it will give me this shape. Now the length of the perimeter will equal the length of this flat surface, and this is L. This L. This time this will give me the surface area. I multiply this one by this one minus K, 2R, and R equal the radius of the cylinder, times pi. This time 2R times pi, it gives me the perimeter of the cylinder, times L, give me the surface area of the cylinder, times dt by dr. Now this is the heat input. Now how about the heat output, Q out? Again, I will use Fourier equation. Of course, this is the heat input to the surface, the inside surface of the cylinder. There is a heat generated within the element. Now, if we follow this equation, this means the heat given from the inside surface of the cylinder, plus there's a change in heat transfer by conduction. This change will be dr times minus K2R pi L dt by dr times di. This change occurs due to heat generated within the element. Now, the heat generated within the element will be Q subscript G. What's the definition of Q subscript G? Heat generated per unit volume. QG, we mentioned this one in the last lecture. What we said this one, Q subscript G, is equal to heat generated per unit volume. Now, if we have a volume, this volume, it would be 2R pi L dr. Of course, it would give me the total heat generated within the element. Now, you might ask this question. You said, what is the volume of the element disturbed? It is easy to say. Now, what I wrote here, I said 2 pi R times L. I could find the volume of this cylinder, a hollow cylinder. I could find the volume of the hollow cylinder by the following method. I could say now the surface area of the base times the height times that, and give me the volume of a solid cylinder. In our case, we don't have a solid cylinder, but we have a hollow cylinder. Therefore, I could find the volume of this hollow cylinder by following the following method. I'd say now surface area times pi give me volume of the solid cylinder minus the surface area of the inside cylinder times I, and give me the volume of this space inside the cylinder. First one minus second one, it gives me the volume of the hollow cylinder. I could say the following thing. I want to find the volume of this whole cylinder. I'm going to say the following thing. I will say the perimeter of this cylinder 2r pi is equal to length, this flat surface. Now L, the height of the cylinder, which is equal to the length of this flat surface. Now if I say this time this, give me surface area of this flat surface. If I multiply by the thickness of this flat plate, it gives me the volume of this plate, which is equal to the volume of this hollow cylinder. I repeat now again. There are two methods. The first method, which is the tedious one, the lengthy one, what we are saying, we say the base surface area of the base times height. It gives me what? It gives me the volume of a solid cylinder. What we have, a hollow cylinder. Therefore, what I'm going to say minus the volume of this space, which is equal to the surface area of this hollow space, times height. First one minus the second one, give me the volume of this material. Or otherwise, give me the volume of this flat surface. Now, I could say another method. The another method, what is equal? The perimeter, this one, which is 2r pi, which is equal to the length of this flat surface, times height, give me the surface area of this flat surface, times thickness, give me the volume of this shape, Now he did the same thing here. You can see now 2 pi r, this is the perimeter, times L, give me the surface area of flat surface, times dr, thickness of the element strip, Now this is the volume of the hollow, cylinder, multiplied by G subscript, which is mean heat per volume, heat generated per volume. This time this to give me the heat generated. Now we follow the same equation. Now I'm going to substitute these statements in the definition here. Input heat to the element, this one, which is equal to this one, plus minus heat generated, plus, and the heat output, give me this equation here. You can see now, this minus this is equal to this. Now when you transfer this from high side to the left side, it will be minus, Now we could cancel some common parameter within this equation easily. Now for example, we could cancel out 2 from this equation. We could cancel out pi as well, pi from this equation here. Therefore, we could have the following. Equation: Q subscript G times 2r pi dr L plus d by dr, this one, because this minus times minus, it will cancel out this with this one. With this one here. Now, we could cancel out similar parameter, we can have this equation here, we can have this equation here. Now, by this equation, again, we could cancel out 2 from here, cancel out here 2, and we could have the following equation. We could have the following equation. The following equation, it would be as follows. Q subscript G times R divided by K plus dt by dr plus R d2 t by dr squared. Now you should follow my statement. I say now R d2 t divided by dr squared. Now don't say d squared. d2t divided by dr squared. This one is equal to not to 0. Therefore, Q subscript G divided by R plus 1 upon R times dt by dr plus dt t by dr squared equal to naught. Now, how did we get this final equation? Now, what we did now, we could say now as follows. If we divide both sides of this equation by k, this divided by k, this divided by k, we would get now, of course, this equation. Now, what he did here, he said d divided by dr of this equation here. I should do the second derivative of this equation now. Now, if you do the second derivative of this equation, of course, you get this one here. Now, what he did now, he divided both equations by r and get this final equation. Now, we cannot solve this equation unless we get the boundary condition. We get the boundary condition. The boundary condition for this equation, we could say it as follows. R equal to Ri. R equal to Ri. What I mean by Ri, it means the inside radius of the hollow cylinder. T equal Ti. Ti equal to inside temperature. R equal to R naught. T equal to T naught, outside temperature. Now, from this equation, we get, if you do this follow solving this equation, we get T minus T naught equal to TQ equal Q subscript G divided by 4K R naught square minus R naught plus C1 ln R naught. We get this equation by solving this equation, and we know the boundary condition, therefore we get this equation. Now, this is a very useful equation. Of course, C1 is, we could find C1, and I'll show you later on, but I could use this equation to find the temperature distribution within this hollow cylinder. Of course, this is my hollow cylinder. I could find now the temperature distribution within this hollow cylinder. What I mean, you could find the temperature, for instance, here. You could find the temperature here, and so on, and so on. How can we find the temperature distribution within this hollow cylinder by carrying the same method or the following method? I assume R. I'll get the temperature, the corresponding temperature, and given R. Therefore, I would carry this method by again and again, assuming R, and you could find T. Of course, T naught is known, which is the outside temperature, K thermal conductivity, Q heat generated per unit volume, and we know that. R naught, the outside radius, we know the outside radius of the cylinder. We should find now C1. We could find C1 as follows. C1 is equal Ti minus T naught plus Q subscript G Ri square minus R naught square divided by 4K divided by ln R1 R0 Ri and then R naught. Now, of course, all the parameters here are one known. All the parameters we know it. All you know K, the thermal conductivity of the material. We know Qg heat generated. Tn, T out. We know that. Ri, where R naught. We know that. Therefore, I could find C1. I could substitute here. And as I said before, assume R, you could find T, and so on. This equation, you could use it, and there's another equation, is a very useful equation. You could again use it. This equation, it will be as follows. T naught equal Q bar R square divided by 4K plus TW. T naught equal outside temperature. Q naught equal T naught is equal to temperature at the center of the cylinder. Q bar heat generated per unit volume in our radius, TW temperature with K thermal conductivity. Therefore, you could find the maximum temperature from this equation. This equation. Now we could go to some exercise. If we follow now, if we go to homework exercise. In homework exercise. Now we solve question number 1. We solve question number 2. What I'm going to say now, I'm going to say the following thing. At the furnace, we have a furnace. The temperature of the furnace here, we know it. Now, okay? The material of the wall of the furnace, we know it. Therefore, we know the physical properties of the material. Therefore, I know the thermal conductivity of the material of this wall. K is well known. K is well known. I could find the temperature here. I could find the temperature here. Okay? Now we use three insulation, three lagging. We use three lagging. Each lagging has its own physical properties. It means that this has a certain thermal conductivity, this has a certain thermal conductivity, this has thermal conductivity. Therefore, I know the amount of heat flowing through this insulation. I know the physical properties of each insulation. I could find the temperature at the interface. Let's consider the following example. Suppose we have a furnace. Now, there is a flame. Or there's a source of heat within this furnace. Therefore, the amount of heat given to this surface is the same amount is given to this surface. The surface is facing you. The surface is parallel to the black part. But if we have the following case, now we assume we have a flame. We have a flame. Now this flame, it will touch or nearly touch this surface. Now we must think about it carefully. Shall I use insulator could stand high temperature? The answer yes. But are we going to use this insulator all the way from here to here? From here to here? The answer is not. I could explain it to you a bit easier. This is the wall of the furnace, and this is the flame. Now you can see the flame facing what? Facing this surface area. Okay? While this surface area is far away from this flame. The temperature of this surface area facing this flame will be very high. Let's say, here is about, we could say now, this is about 800 degrees Kelvin. While this place here, it will be the temperature about, let's say, 500 Kelvin. Now, my question, shall I use lagging or insulator the same all the way from here to here? The answer no. Why? Because this insulation will stand high temperature, 800 Kelvin, it will be very costly. Therefore, do you know what I use? I use it from here to here. Insulation could stand 800 Kelvin. While this face from here to here, I use different insulation to stand 500 Kelvin. Now, if you look to the question, number 3. This question number 3. Now we cannot solve this equation the same way what we did with insulation have the same properties, which is R in series, شوف اشرح. We are going to do the following thing. راح نسوي شيء تالي. سؤال شوي تقول انه كلش مهم هذا. راح نحله نسوي سلام. خلي شوي ابدي وبعدين احكي. Now what we're going to say. Now what we say if the resistors now resistors and power mat are in series. Resistors insulator are in series, as we said here.